Hi guys, in this session, we're going to be building a simple reinforcement learning algorithm. But like we always do, we'll go through the notes and then we'll code. So in our previous session, we've been able to see how we can build a reinforcement learning um, pattern or build a reinforcement learning value function using hard-coded rules. But in this session, you're going to see how that can be replaced by neural network. So what happens here is the network starts with nothing. I mean, it starts with no value policy. So and then after each episode, it's keeps moving towards action that gets it better rewards. So over time, it nudges away from actions that got low reward, and then when it repeats this uh, number of times, maybe thousands of times, it truly learns what action actually gets it higher reward, and that's the essence of reinforcement learning, like we discussed before now. Okay, so I'm going to list the actions that the agent is going to need to take uh, across the episode. Here is reinforce. Building simplest uh, RL algorithm. Okay. So now what are the steps you are going to be taking towards achieving that? So I'm going to list that in 5 steps. So RL so now the first step is to run an episode. And like we've always done in the previous examples, we know that in each steps taken, in every those steps, there's always an action that is passed towards it. And that action, be able to collect the next state, be able to, get the actions and the rewards. Okay. So in the first thing we will do is we'll run an episode using the current policy. So say okay. So when we run the episode using the current policy that we have, okay. So what we collect is we collect the states, the action, and the rewards, right? Now the next thing we do after this is that we compute the returns. We compute the returns for each step, and if we do not forget, in our last session we looked at how the return can be computed, using the discount factor as well and all of that. So we talked about the optimal value that can be used for the discount factor as well. So this is what we do. So here, compute the return GT. Okay, and we do that, using the backward pass. So, and I think one thing we've been able to also establish in our last session is that, computing the return using the backward pass is better. Now, the third step we'll be looking at here. Now, the third step we'll be looking at here is to normalize the return. Okay, so that's normalizing the return. That's just like taking the return, subtracting it from the mean and dividing by the standard deviation. So that's basically like normalizing it. Okay, so we normalize. And why do we do this? So we do this to ensure that the gradients, update at a consistent scale. So we don't want unstable gradient updates. So unstable gradient updates, will affect the learning of the model, when especially during backward propagation. We want minute and stable updates. We don't want exploding gradients. We don't want diminishing gradients, or we don't want unstable gradient updates. So what we want is a consistent gradient update of this model, more especially during backward propagation. So here, what we say is we normalize the return. G, so that is the G minus mean x bar divided by sigma, and that's basically uh, uh normalizing this. So then the next thing we do, normalizing the return. The next thing we do is we compute the loss. Okay, we compute the loss. And to calculate the loss, we say minus log minus summation, sorry, log of policy. Okay, and that is for a given that's a loss of a given loss of the log of the policy of the action at a specific time given states. Okay, times the return. Okay, so we talk about log probabilities as well. So which returns the probability function of the actions to be taken given state and not just a deterministic approach. I think that's also one of those things we discussed in our previous sessions. So we can really understand why we are taking log probabilities here. And also we talked about why to choose the negative sign. Why put the negative sign there? So we said that's to minimize loss and to maximize reward. So then the next thing, is back propagation, and then optimizer. Optimizer. So I believe if you are not new to PyTorch, you must have seen this when training any PyTorch module. So look at what the neural network will look like. So in the neural network, so don't forget that we have the input layer. So this is where we are going to feed in the architecture. It's the data, the input data we are putting in. So here we have the inputs. And within these inputs, we are having some important information such as the cat position. So we talk about the cat position, we talk about the cat velocity, talk about the pole angle, and pole angular. I hope this is written well. Velocity. Okay, so that's the input. So then after that, we have the linear layer. So this linear layer, what it basically does is just project um, a full feed-forward neural network, which is a fully connected neural network. Okay, so since we're having 4 inputs here, okay, so this feed-forward neural network, which is a fully connected neural network, so we're projecting 4 inputs to 128 uh, uh, 28 units within this layer. So, and here we are going to also, don't forget, in a neural network, at the end of each layer, there will always be a nonlinear transformation. So, so sorry, if this is a linear transformation, if linear is performing linear transformation of the input data, you also have a nonlinear transformation, and that is to ensure that the data that is being passed into it is being well handled, and I'm going to explain. So here we have ReLU. Now, what is ReLU? So ReLU is a nonlinear transformation or an activation function, often used, in the deep layers of neural network. So what ReLU does is, ReLU is one, okay, or let me say, it is the max of 0, z. So let's say z is the output of the linear transformation. So ReLU takes it and it returns the max of 0, z. So what happens is, if this value is greater than 0, then this value goes. But if it is less than 0, then ReLU goes for 0. ReLU goes for 0. That is that. So if you look at a graph like this, for example, this is ReLU. Okay, ReLU, let's say rate units. So what this does is, for non-positive numbers, so this is the x-axis, is negative x, is positive x. For non-positive numbers, so it returns 0. This is 0, like 0. But if the numbers are positive, then it returns them. So what that does is, it helps to smoothen the value that is being passed into it. Very helps to smoothen the values. So it helps to smoothen out noises and return real positive numbers. So now the next thing we have outside of that is also another linear layer. And here you have 128, 128. And then we use ReLU as well. So that's 128 linear units, 128 linear units. And then we also have another linear layer here as well. But this is for the outputs. This is for the output. Okay, so here, since 128 is being passed out, so we'll be picking on that 128, and then we'll be having 2 layers on the outputs. Now, what we are going to be using here, we're going to be using softmax. Now, what is softmax? So softmax is also another another activation function. So what softmax helps us to do is to return output probabilities. Output probabilities. So now that we are going to be having 2 values here, 2 values in the output layer. So what that will help us to do is, so let's say we have A and B, for example. So these are the 2 values that is returning the output probabilities. So it will help us like redistribute those probabilities into those two numbers in such a way that at each time it will tell us that okay, the probability of going for A given what we have is maybe 65% and going for B is maybe 35%. Okay, so we know what to go for here then, right? Given these two values. And this makes sense because at the output layer, we want to take an action. In this case, we have only two actions to be taken. Action to go left or to go right. That is to shift the cards. We have the cards here, and we have the card pole here. So to shift the position towards right or to shift the position towards left. So those are the two decisions we want to take. So, and that is what this output layer helps us to takes the decision on what to do at each time step. So that's softmax that is going to be, returning that there. And then, that will be the output. That will be the output, of what to do. So maybe to go left or to go right. So that is basically that. So, well, basically here, I'm just using this percentage as an example. It's returning output probabilities. And what that is going to be is that the sum of the values that it will be returning here is going to be equal to 1, right? So it's not going to be returning 65. It will be returning maybe like 0.65 and 0.35. So, that's going to be summing up also 1 or any other similar value. And that's so you use softmax when you are classifying, okay? Because in this case, you are basically classifying what category to go for, or what is the best category to go for, or what the best category fits given the values that you have. So, okay, I want to give an example on softmax. Okay. So, because I've mentioned that software is often used, for classification, here it's going to be telling us what category to go for given the values that we passed into the neural network. So, and what it does is that raw network outputs, can be any number. It's a positive or negative. That is what we are computing in the linear layer. Okay, but softmax help us to convert those, raw outputs, those raw numbers, into output probabilities that sum up to 1. And that's what I explained just here. So an example would be maybe during this linear layer, we could have something such as, let's say, um, raw output. Raw output could be something like minus 0.5 and 1.2. Left, right. Now, so what softmax is going to do, so softmax is going to convert this raw output into non-linear transformations with our softmax here. So we're having something like 0.17 and 0.83. So that is what softmax will be doing there. So softmax also has its own formula. Okay, so you can say the formula of softmax is softmax is represented by this. Say zi equals the exponential z I divided by summation g equals to 1. Is starting from 1. Exponential up of t exponential z. Okay. So basically, we're able to compute the softmax of these two values here. So you'll be having this, which are the output probability of what you have there. So that's that. So we are going to be looking at the gradient update of two scenarios. Okay. So let's say, for example, that uh, log probability of a given action given a state s equals to 0.5. Sorry, minus 0.5. Minus 0.5, right? Now, and the return g equals, let's say, 200 plus 200. That's the return. Okay. So the loss contribution, and don't forget that we mentioned during our loss calculation for our loss, I said the loss equals to the summation of log probability of a given state given its action times the return. So here we are going to say, since we know that loss equals to is minus summation log pi of at given st times the return gt. So you say the loss equals minus 0.5 times 200. So here you get minus 100, right? Oh, sorry. Oh, we have a minus here as well. So here we have plus 100, right? You have plus 100. So that's the loss. So here is the loss contribution. Okay. So now the second scenario we'll be looking at is this. The second scenario we'll be looking at is this. So so let's say log is a log pi of a given s equals minus 0.5 and the reward g equals plus 5. So in this case, the loss contribution equals to minus 0.5 times 5. So we have, is that 2.5 plus 2.5? So you can see that after updates, probability barely changes. The probability barely changes even after updates. And that's one of the lessons we'll be learning from here. Hi, so we're able to see how we calculate the loss contribution of each of these um, outputs, values from the neural network layers, and we're able to see how, the probability barely changes, even when we calculate the loss contribution, for the one with higher returns, has higher loss contribution, and then the one with lower returns, has very lower contribution. So yes, that's okay. So I think I've also talked about normalization, or why we normalize, the returns, and that's because we want stable values. So just imagine, having values such as, maybe having G to be equal to maybe 200, 190, 190, 180, and so on like that, right? So these are quite, uh, big updates. So the gradients on each of these are quite big, will lead to big updates, which can destabilize training. So when during backward propagation, when the gradient is too big, that can lead to exploding gradients, right? So we don't want that. We want stable gradients that are not too big, neither are they too small, but are just stable, and they can ensure that our model um, learn appropriately, they learn consistently. So we don't want gradient updates that are just too large at a point. That would destabilize our training. So once gradients that increase, we want gradient updates that are small in size but consistent in learning. Okay, when it is small and consistent, then we can be sure that the model is actually learning. So then also, I believe for learning rates as well, when we talk about learning rates, LR, because this is deep learning now. So when we talk about learning rates, okay, no, what's yes, always. Okay, so we call this minima, right? So we want to ensure that our learning rate is small, such that we can get to this global minimum. So if it is large enough, it will, I mean, it's just going to be taking larger steps, and then maybe it can offshoot the global minimum and then return. But if it is small enough, it can be taking smaller steps, baby steps, that can ensure that at some point we definitely get to the global minimum, right? So once our LR should be small enough to get to global minima without or shooting. Okay. So once you want a learning rate that is just small enough, so maybe something like 1 exponential minus 3, that's 0.003, right? Oh, 001, 003, 001, right? Something like that is okay. Okay, so that is basically that. So now we are going to look at this in code. Okay, so you're going to be um, writing our code now. So here we'll be using PyTorch. So if you don't understand some basics of PyTorch, I would advise that you do try to understand them. But I think if you are patient enough and try to, follow through, you might understand. Okay, so the first thing we are going to do is we are going to import required libraries. So here we have Gymnasium, which is what we are using. We have Touch as well. That's for PyTorch. We have Touch.nn for constructing our neural network layers. We have Optim for optimization. We have this uh, for categorical distribution, which we are still going to see. We have NumPy and Matplotlib, NumPy numeric analysis, Matplotlib visualization. So the first thing we are going to do is we are going to build a neural network class, okay, and that's how PyTorch works. So inside of this class, we are going to pass in nn.module. So this enables us to inherit PyTorch properties of creating a neural network. So then we are going to self-initialize our class. So we are going to pass all of our layers into this sequential layer. So here we have, so sequential because it is left to right. So sequential layers are layers that are, left to right, layers, and that's for the input to the output. So that's that. Don't forget that the inputs at the inputs layer we have four inputs, so which we are going to look at. So you define that here with OBS size as observation size, and then the output as the hidden. Oh, we have the hidden layer, and then we have the activation function like I mentioned. I just copy this. So now, then here I'm going to have hidden. If hidden is the output of the previous layer, then hidden will be the input of the next layer. Then here as well, so red will be the output will be the linear transformation for the second layer. So for the third layer as well, so hidden is the output of the second layer. So hidden will be the input of the third layer. So here I might have action size being the output here. That's what I'm using render for here. Then I'll have a feed forward function. So this is how we are going to implement our softmax. So we have nn.functional, the softmax. So here we pass in the logic into it. Equals -1. So yes, that is that. So this is basically, so what we just did here is this. So we defined the values that we're going to be using within the class. So here we have the OBS size, direction size, the action size, and the engine layer. So basically, in the inputs layer of our neural network, so we are going to be feeding the inputs value into it, which is the core parameters, the cat's position, the cat's velocity, the pole angle, and the pole angular velocity. So those are the four observation states that are going to be passing into the neural network. Then the hidden layer as well is 128 units, so which is that. The 128. So since this the output of the previous layer, the first input layer is 128. So the input of the second layer will be 128, right? So then output 128 as well. So since this is output 128, then this is also taking in 128 as its input and then outputting the action size, which is 2, deciding on which uh place to go, left or right. So that's that. Now, so this X represents the input that is going to be passed. So it's going to pass it to this, and then we compute the softmax of this. So that's basically what we've done here. So maybe you may want to even do some little things. Yeah. So I may want to call this function policy network, right? So I may have maybe just a state. So let's say this is an observation state, for example. So here are the, let's say the four observable states we have. Okay. So then we decided to use, I mean, this is a float data type, so that's what we are using. So I want to, pass this state into the policy. So I'm going to say, so, and don't forget, so this is it. These are the states, right? One, two, three, four. These are the four observation states you are passing in. So we pass in for observation state. Don't forget that the initial state to interact uh, with the hidden layer, the neural network, and then the hidden layers, and then the hidden layers output uh, probabilities, right? The output values. So it is those values that we convert to softmax, be able to know, the output probability, the probability of what direction to go. So let's say the action state equals so policy. Then I'm going to pass in this mock state into it. Now let's take a look at what this is. Action state. So let's take a look at that. So let's wait for this to run and see. Oh, okay. Sorry, PyTorch just not installed on this flat environment. Installed or installed. Okay, so we can now check what the output here is. We are done with the installation. Okay, so it's saying the descriptor needs an argument. Oh, sorry. I think I made a mistake here. I made a mistake when I put in there. Oh, great. This is beautiful. So you can see, so this is the output probability we are getting here. So for left, you are getting 0.85, and then right, you are getting 0.95. And then this is, the output probability that softmax is returning, right? This is the output probability softmax is returning. Let me copy this and return the logits to see what that would look like without softmax. Let's see what that would look like without softmax. Yeah, so without softmax, so you can see this is minus 0.1, a 0.1 minus 0.03. So this is what the neural network is producing at the output layer, so which is then picked by by softmax to convert it to this. So that's basically that. So I just wanted you to, like, see how that works without softmax. Okay, so let's proceed to that part of our code. So we are going to we are going to get a function that train a single episode. Okay, so here is a function that trains just one episode, right? So we have that here. And then also you have a neural network, a neural network function, So because we want to train with neural network, so here we are going to have a function that helps to train with neural network here. That's the train with neural network. And then we have our graphs. We're going to define function for plotting graphs. Good. So here is a function. I mean, here is an environment for the CartPole, so which is being optimized using the neural network. So we use the neural network to calculate the value policy and all of that. So here we are going to run the functions. Let me just walk you through them. So here is the neural network. Here is a function for a single episode. Okay. So once we train on a single episode, this is what we get, and it returns the reward. So here is a function that um, trains the neural network, trains the CartPole with neural network. So within that, we run a single episode with neural network. And here we are plotting a graph that compared the different learning rates. I talked about learning rates effect the other time. So see the effect of that on the model itself. And here is the function that plots the training curve. So we also see that as well. So let's run this and see what we have here. Okay, so here is what we have. So we have this training reinforce. So at episode 0, we have reward 14. At episode 50, we have reward 79, and average reward is 37. At episode 100, reward is 135, average is 111.7. So that's basically like getting, much more reward with time. So it's learning. That's basically, shows that this is actually there. I would like to see some graphs. Okay, still learning. So here's episode 150. So you can see here the reward is 165 and the average reward is 228. So here is the graph. So we're able to see across the episodes, what the average reward looks like. So at some point we saw that, it peaked and then, it's returned down, right? So that is that. Yeah. Okay, so that is that. Um, so let's take a look at these two learning rates and see what the average episode looks like. So you're able to see for when the learning rate is exponential -2, see it's quite large. These are the average reward, but the reward is even reducing with time. When the learning rate is, exponential -3, since it's optimal, so you can see they are increasing with time. So let's see what we have on episode 2. So then here as well, we see what the learning rate is when it is quite large, -4, exponential -4. So you can see -2, exponential -2, you can see it's quite small, right? This is the average learning rate here, very, very small. -4 is too, quite large, right? So this is too small. And then for this seems optimal. So you can see the average learning rate here seems optimal, right? So that's that for the learning rates, right? So I believe from here you can see that picking an optimal learning rate, not too small, not too large, is best when training any deep learning model or anything that involves deep learning. So I hope with this you've been able to learn one or two things. If you've done, kindly like, subscribe, and share this video to your loved ones. Thank you.